This video is about the need for a different address space in the network layer. At first we investigate whether a flat address space, which is just a series of numbers, is suitable for it. In such an address space it is possible to distinguish between end systems, because the addresses can be assigned in a unique manner. This holds in reality for the MAC addresses which are assigned by vendors in the production process. We can take a look at the drawing on the bottom of the slide to find out which knowledge is needed for switches to forward frames in a local area network. You can see that in the bridge table entries are needed for each end system, in this case for the MAC addresses of end systems A, B, C, D, E, together with the respective port numbers. If there were much more end systems, then it would be necessary to learn and administrate entries for each of them, so that there would be scalability issues. It is possible to compare the situation to a real-world analogy. Let us assume that in a country there are ID cards for the citizens and each ID card has a unique number. If you want to send a letter to a person, you write the ID number on the envelope. It would be unique who the destination of the letter is. However, it would be very inconvenient to determine for the postal service, because long lists containing all people with their IDs and where they live would be required. The misconception is that the addresses are not location dependent. In summary, we can conclude that there are scalability issues when using such a flat address space for a large network. Search tables in the devices would be large, resulting in long search times and large memory requirements. In addition, a lot of updates are necessary to keep tables up to date everywhere in the network. Therefore, flat address spaces are only useful in local area networks. A scalable solution is a hierarchically organized address space, which can also be regarded as location-dependent address space. We find such address spaces, for example, for postal service zip codes or telephony numbers. Telephone numbers start with a country code like +49 for Germany or +1 for the United States, followed by an area code and a local number at the end. This has the major advantage that knowledge can be distributed. For instance, in Germany, it is only necessary to know how to direct a call to the United States, but it is not necessary to know how networks inside the United States are organized. In the figure, we see an example of networks and the routing tables of two intermediate systems are shown. Router 4 only knows that it has to forward data to routers 5 and 6 to reach the networks 2 and 3. But it does not have to know the details of subnetworks within networks 2 and 3. So, for example, it is unknown that there is a subnetwork 3.1 and an end system 3.1.2. This method scales very well. All end systems at a certain location get the same address beginning, which is called the prefix. Therefore, only the prefix is relevant for pathfinding, so that intermediate systems only have to process it and can ignore the rest of the address. It is also possible to aggregate information. If there are, for example, the networks 1.1, 1.2 and 1.3, then this can be aggregated to just network 1, which is announced to other networks such as network 2 and network 3. The hierarchical organization of addresses makes it easy for different organizations to work together, because each organization can administrate its network on its own. In reality, IP addresses are used in the network layer, where routers just have to process the so-called IP prefix.